So welcome to the second half of calculus. So in the one sense, well, we're 3 months in and we've only got a few weeks left. What's going on? Well, we've done a lot of the heavy lifting for this, as we'll see by the time we get into section 5.3. We will see that we've done most of the heavy lifting that we need. We just need to develop the vocabulary, we need to develop the terminology, the notation, and then we can rely on some of our skills from the first half of this course. Okay? But we're moving on. So there are really two big questions in calculus, and we've answered the first one. We've explored that in great detail. The first one sort of had two parts. How do I find the slope of a tangent line to a curve at a point? And how do I talk about instantaneous rate of change to a curve? And that's what we discussed through this first half of the course. Okay? And we answered that essentially by computing the what? Derivative. By computing the derivative of a function. Okay? So that is essentially the first half of calculus. There's differential calculus, and now we're getting into the second half. So the second question that we want to talk about, and I'll try to motivate our reasoning here towards the end of this lecture as to why we're interested in this. But the second question that we want to ask is, how do we find the area underneath a curve? And this is determined by computing what we're going to call the definite integral. Of a function. Okay? Word integral should be ringing a bell, but we're not quite sure how it's all connected just yet. Okay, so for the area problem, first of all, let me say that there will be times where I'll just ask you to pull upon your normal understanding of geometric shapes. So if it turns out that this curve has a triangle shape to it, you can just use your area for a triangle. Or if it's got a rectangular shape to it, you know how to calculate the area of a rectangle. Or if it's got a semicircle shape to it, you know how to compute the area of a semicircle. Okay? So you can use your basic geometric shapes, and sometimes you'll be saying, oh, I can't figure this one out, and then you say, oh, of course, I just used this basic shape. Okay? So let's go ahead and look at this one here. We're asked to find the area underneath the curve, and I guess I should add this here, and the x-axis. From x equals 2 to x equals 8 for this function right here. What is this function right here? F of x equals 5. What does that function look like? It's a horizontal line, right? So here it is. Here's the graph of it. Maybe something about like that. Okay. There's the graph of f of x. And we're asked to find the area underneath this curve from x equals 2 to x equals 8. So we're asked to approximate this area. Well, not to approximate it, let me be clear. We're asked to find the exact area underneath this curve right here. Well, this is one that is just a geometric shape, right? What's the area underneath this curve? The area underneath this curve is 30. How do we get there?
6 times 5.
So the height of this is 5, and the width of this is 6. And I want you to think of a rectangle as a base times a height. So the area of a rectangle equals a base times a height. Okay, so in this case, the base is a base. Actually, let me just, for fun, let's change that around. Let's say height times a base. Height times a base. Okay. So what was the height of this? The height of this was 5, and the base was 6. So the area is 30 square units. Okay. I think you'll be doing well in this unit if whenever you see a product of two numbers, you go ahead and think of a product of two numbers as an area. You could always create a story problem where you're calculating area based on of a rectangle based upon those two numbers. So that might be helpful for you going forward. Okay. But here's the rub, right? This is what we're really interested in, not finding the area underneath the rectangle. Okay? But how do we approximate the area between this curve, f of x equals x squared and 3, and the x-axis? From x equals 1 to x equals 9. Folks, there are times where I will maybe forget to approximate the area between this curve and the x-axis. But if I say find the area beneath the curve, that's what I'm talking about. Okay? So we're asked to, so notice here, and this is extremely important for these next couple of units, or excuse me, next couple of sections. Pay attention between when you're asked to approximate the area versus find the area. Okay, if I'm asking you to find the area, there must be some way to find the exact answer. If I'm asking you to approximate the area, you're going to use one of the approximation techniques we're going to learn in this section. Okay, so do pay attention to that. Okay, and we're going to approximate the area using the left endpoint method for 4 rectangles. Okay. All right, folks, I know some of you have done this before. Some of you, this is brand new. Okay, I wish everyone came into this class with this being brand new. Okay, because it's an interesting thing to do the first time. All right, we're trying to find this area right here, and I will actually shade this. You don't need to. This is just for illustrative purposes. We're being asked to we're being asked to come up with a guess of what I've shaded in red right here. Okay, I don't recommend doing this because we're about to. I can do this because I've got these multiple colors and stuff. So maybe, you know, if you do it oh so lightly. Okay. All right. We want to approximate this area underneath the curve here between x equals 1 and x equals 9. Okay. We are going to approximate this by breaking it up into segments and then matching a rectangle to each one of those segments. Integral calculus starts off by using rectangles to approximate area underneath the curve. Right, that's how this starts out. So we want to use, we're told in this problem to use how many rectangles? 4. Okay, I want to go ahead and let's just right away, let's start introducing some notation here. Okay, so we're going to call the width of each rectangle in fact, let me call that the base of each rectangle. The base of each rectangle, we're going to call it delta x. Okay? The choice of that notation isn't clear yet. Okay? But we'll use delta x to be the base of each rectangle. Okay? And delta x is equal to b minus a over n, where b is the rightmost endpoint, a is the leftmost endpoint, and n is the number of rectangles. Okay? So in this problem, what was the rightmost endpoint? 9 minus the leftmost endpoint, which is 1, all divided by the number of rectangles we wanted, which is 4. So this gives us 8 divided by 4, which is 2. Okay? So the width of each one of these is going to be 2. Okay? So let's go ahead and start. Let me be a little more careful there. Let's go ahead and start. This will be my first rectangle between here and here. Oops, that's not true. Between 1 and 3, right? That'll be my first rectangle. Then my next rectangle will be something between 3 and 5, and then I'll do 5 and 7, and then 7 and 9. Does everyone see that? This gives me, you can see how I've tried to draw these larger dashes here. That gives me how many regions? 4. Okay, let's start stressing this right away though. I've got 4 regions. How many tick marks have I made? 5. This is important. Okay. If I want to break something up into 4 segments, I need how many boundary markers? 5 boundary markers. Okay. So if you want to think, I think this is helpful. If you wanted to make 4 sections of fence, how many fence posts do you need? 5. Okay. Some of you will mess up on that. Don't worry. I've been to the lumberyard more than once on one day as well. Okay. So you need 1 more post than you do sections of fence. Okay. So keep that in mind. All right. So right here for this first region, I want to construct a rectangle that somehow matches the area of the curve. Okay? Well, what I'm going to do is I'm going to go up until the left endpoint intersects the curve. That will be my first rectangle, and I'll shade that green here. There's my first rectangle that I'm using to approximate the area beneath the curve. Okay? And I'll draw the second one in a minute, but here I just want to emphasize what we're doing here. So let me draw I'm going to jump out of order. Normally you wouldn't do this. I'm going to draw this third rectangle here, and please don't write it down just yet. Okay? So one way I could construct this third rectangle is like this. That's one way I could construct this third rectangle. What did I do here? Well, I drew a rectangle that rose up until the right side of it intersected the curve. That's called the right endpoint method. Okay? Well, that's not what we're being asked to do in this problem. Okay? There are many other ways I could do this. I could go up until the midpoint of the rectangle intersects the curve, and then construct the rectangle like this, and that would be called my midpoint method. Okay? But we're not asked to use either one of those. By the way, there doesn't actually have to be a rhyme or reason. I could pick some random x value in here, call it x star, and it's inside the third interval, and I could go up to where this point intersects the curve, and that's where I make my rectangle. Again, you don't need to write that down. We're not going to do this yet. But I just want to show you that there are different methods for doing this. Okay? All right, but here we're specifically tasked with using the left endpoint method. So here's my second rectangle.
You don't go above that curve at all, right? To hit up the next. Like,
Well, if you remember when I did the right endpoint method, I did.
I just meant for the left endpoint.
So here's how I want you to think about it. In this case, no, you're exactly right. In this case, I'm never rising above the curve.
Okay.
But that's actually specific to the curve itself that we're dealing with.
Okay.
And I'll have you make a hypothesis on that going forward. We'll keep thinking about that question because it's a really good question. And yeah, you're right. In this case, I will never make a rectangle that goes above the curve, but that is not because of the method that I'm using per se. It has to do with the structure of the curve itself. Okay? All right? And so then for this fourth one, we go up till the left endpoint intersects the curve. And there it is. Okay? Pretty ugly. I think you can follow your way through it. Okay. So, any questions on this? So if we want to approximate the area underneath the curve, all I need to do is take this base times this height, and add to it this base times this height, add to it this base times this height, and the last rectangle as well. We're going to be summing up the areas of a bunch of rectangles. That's what the second half of calculus is about. Summing up the area of a bunch of rectangles. Okay? So, one thing I want to do right away is you will not always be able to quickly graph the function that you're working with. Okay? So, I think that you should always draw yourself a picture for these problems. It doesn't have to be an accurate picture. So let me show you what I would do if I were tackling this problem. Okay? If I didn't have this graph sitting right here, what I would do is I would go ahead and just give myself some arbitrary function that looks like this. Okay? It's usually a good idea. In fact, I'm going to change that. It's arbitrary, but I like to have it be kind of steadily increasing or steadily decreasing, just so my rectangles don't overlap in weird ways that are hard to look at. Okay? Then I go ahead and put my left endpoint, which was 1. I put my right endpoint, which was 9. Then I use my delta x to construct all the other intervals. Let's see here. Delta x is 2, so 1 plus 2 gives me 3. 3 plus 2 gives me 5. 5 plus 2 gives me 7. You see how I'm basically getting the same picture, okay, building it from scratch. And I'm not actually concerned with what the function actually looks like, but this is the critical part. Okay? I'm now going to draw the rectangles, and even though I don't care about what this graph looks like, I'm going to use the correct method when I draw these rectangles. So here we go. We're going to go up to where the left side of this first region intersects the curve. That's our first rectangle. Then we go up to where the left side of this region intersects the curve. And we do that for all of these. Okay? So for the rest of this problem, I'm actually going to look at, you can look at this picture. I'm going to look at this picture to finish out the rest of this problem because that's really what you'll be doing on your own. Okay? Here we have the actual graph, but generally we don't have that in front of us. Okay? All right. So not a lot of room down here at the bottom, but we'll get it in. All right. So we're going to say that the area underneath the curve can be approximated using the left endpoint method. I'm going to put an L there. For the left endpoint method, how many rectangles do I have? 4. So I'm going to put a subscript 4 there. Okay? That's my choice of notation. Some books use it, some books don't. Okay? So now pay attention to when I use the equal sign versus the approximate sign. Okay? We're saying that the area underneath the curve is approximated using this method. That makes sense, right? We're not going to get the exact area underneath the curve using these rectangles. Okay? But how would we do this left endpoint method? Well, what we're going to do is we're going to take the functional value evaluated somewhere in this first interval. Well, because I'm using, here's my first interval, right? So I could pick, for this first interval, I could pick any number between 1 and 3 to give me the height. But because I'm using the left endpoint method, what value am I going to plug into the function here to get the height of this first rectangle? 1. So I'm going to take f of 1 times delta x plus, then I'm going to take f of what? Yeah, f of 3 delta x. Notice I can get all of this from this inaccurate picture on the far right here. From this inaccurate picture, I can get all of this information. Okay? Plus f of what? 5 delta x plus f of 7 delta x. Folks, breaks my heart if you then write f of 9 delta x. Why is this wrong? At just the most superficial level, why is this wrong?
Because you're evaluating it outside of the interval.
Well, I mean, here's a 9.
But it's left.
Delta x is
Outside
0.
of the interval, because it's left endpoint, so the
Well, but here's the interval, right? So the interval did go for, here's an interval that goes from 7 to 9. You're on the right track. Okay, I just want to tell you there's a much, I think that all of your responses for as to why that's wrong are just fine. Let me give you just a much more obvious one. We're adding up how many rectangles here? 4. How many rectangles? I've got a base times a height. A base times, excuse me, a height times a base. 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 There are the 4 rectangles that I was asked to add up. Okay? So I do not want this 5th rectangle here. Okay? Great. So if you plug 1 into this function, let's see here. Well, it's 1 squared plus 3. So I think we get 4 times 2. Right? Then adding, well, we plug 3 into the function. Let's see. I think we get 12 times 2 plus 28 times 2 plus 52 times 2. Everyone see how we got those? How did I get that last 52? So we plugged the functional, we plugged 7 into the function, right? Okay. So what we did here was we said, hey, this height, this is the ordered pair right here. This is the ordered pair 7, 52. And we took that height value on the function to give us the height of this the last green rectangle. Okay? If we add up all of those, we get 192. Okay? Let's just be kind of cute here. Let's put units squared. Okay? Just to remind ourselves that we have just computed the approximate area underneath this curve. Any questions on that? Yeah, Maria.
Would the area be closer if we did a right?
Great question.
Or left endpoint?
Yeah, so we're going to do the right endpoint method on this in just a second. The question of which one's closer is a really interesting question that we're not going to get into in this class, because neither one of these are going to be close enough for what we want. If you're really interested, after we get going through this, ask yourself something about the concavity of the graph, and that might help you see better which one's a better approximation. Yes?
Why did we choose delta x? Did we choose it to be that, or just how did delta x to
Well, so we didn't choose delta x to be 2 at face value,
be? Yeah.
but we did say we needed to use 4 rectangles.
So, okay, but if we did it with like less rectangles, wouldn't it be closer to?
Yeah, everyone here. We're supposed to be approximating the area underneath the curve, right? We used 4 rectangles. What if we used 6? What if we used 8? What if we used 100? 1,000, 10,000. Oh, I can see where this is going. Right? I can see where this is going. We want to let the number of rectangles increase arbitrarily. Right? That's where we're going with this. Okay? We got a lot of notation to do before we can do that. Okay, so let's go ahead and keep going. We're just going to keep working with this problem. It's kind of a touchy-feely introductory lecture to this. We're going to, again, approximate the area underneath the curve. F of x equals x squared plus 3 from x equals 1 to x equals 9. We're going to use the right endpoint method. Okay? So I want you guys now, and hopefully you got somebody sitting next to you, go ahead and give this a shot. Okay? Give this a shot. You're gonna mimic everything except for your rectangles. In fact, I'll help you out. Let's draw this first rectangle here. My first rectangle will be this rectangle right here. All right, give it a shot. Oh,
That's right.
I have 2 more 5-1 copies. Someone need a copy of 5-1?
Yeah, I gave it.
You disagree or tests?
Yeah.
No. This second rectangle then would look something like this, right? And then here'd be the third rectangle. And then last we get the fourth rectangle. Okay, folks, this is good practice. I want you to keep working through this. I'm going to keep, as each time we go through, I'm going to kind of step up the level of rigor as we go through this just by a little bit. Okay. I want to return to our fence posts that we talked about. Notice that in this problem, are our fence posts different than they were in the last problem?
Yes. Well,
I don't think our fence posts are any different, right? I don't think. So we're going to give this thing a name, okay? I'm going to say that what we just did is we partitioned the region, okay? We partitioned the region into, we partitioned it with how many values? We partitioned it with 5 values, okay? So we're going to say here that our partition would be, so what was the first one? Well, let's go abstractly first. We're going to start counting at x0, x1, x2, x3, and x4. Those are the 5 values that show up in our partition. Folks, this is going to be challenging for this section. In math, you can start counting wherever you like. Counting is just a sorting procedure. Watch. Okay? -3, -2, -1, 0, 1. Right? I just enumerated these 5 items in a sequential way. Okay? Oftentimes we will count for our partitions. We will start enumerating the values in the partitions at 0. And we'll see why as we go along. Okay? Anyway, here are the 5 values in our partition. The 0th value is 1, then 2, then 3, then 5, then 7, then 9. Okay? So this is 0, 1, 2, 3, 4. Those are the 5 values in the partition. Okay? Now, the reason why we count them that way is because that enables us to make the intervals count the way we would expect to count the intervals. So the first interval goes from 1 to 3. The next interval goes from 3 to 5. The next interval goes from 5 to 7. And the last goes from 7 to 9. At this point, we have at no point introduced the idea of using a left endpoint method or a right endpoint method. The choice of intervals is independent of whatever method we're doing. Okay? That's why, in fact, that I'm not using what's here to denote my intervals. I'm not using what symbol. I'm not using parentheses, I'm using brackets. Okay? So then, when you do this procedure, what you do is you pick one value from each interval. You can be completely random in how you pick a value from each interval, but it's nice if you do it methodically. Okay? In the last problem, what did we do? We picked these values. We picked 1, 3, 5, and 7 to evaluate in the function. Which values did we pick? We picked the left endpoint for each of those intervals. In this problem, we're going to pick what? The right values, 3, 5, 7, and 9, using the right endpoints of the intervals. Okay? This abstract way of doing this problem is really helpful when you have graphs that you can't really work with. You have extremely complex functions, you can still do this procedure. Okay, so now we're ready to approximate the area underneath the curve. So the area underneath the curve can be approximated using the right endpoint method with 4 rectangles. Okay, really it's just 4 intervals. Okay, and we say that we're going to take, here again I'm going to do this a little abstractly, I'm going to do f of x1 delta x plus f of x2 delta x plus dot dot dot, well, it's kind of silly to do dot 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 at that point. I'll step back a little bit. Plus dot 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 plus f of x4 delta x. Okay, what does the dot 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 mean?
So on and so forth.
Yes and no. I like the dot 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 to mean that you should have been able to pick up on the pattern that's going to be going forward. Okay? So for instance, you would never write 1, 27, or 2/7, -3, dot dot dot, right? That nobody knows what's going on. It does continue, but how? So the dot 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 tells the reader you should be able to pick up on what the pattern should be. Okay? Okay, but this, let's be more precise. This would be f of 3 times 2, because our delta x hasn't changed here, right? Okay. Plus f of 5 times 2 plus f of 7 times 2 plus f of 9 times 2. And when you crunch that, what do you get? You get something like 352. Great. Okay.
Units.
Yeah, units squared, being a little pedantic, yeah. Okay. So, notice that in the last instance, we had an underestimation of the true area, and in this one we have an overestimation. At that point, I mean, you could say that we know the area of the curve to be somewhere between 192 and 352 units squared, but that's not very good, right? But we've developed the method that we need. Now we just need to refine that method. Yes, what do we want to do next?
Like if we were to take an average between the two numbers, is that going to give us like more approximate?
We could do that. You could take the average of the two and get a better approximation. That's perfectly fine.
Mean value.
Ooh. Ooh.
Was way off, sorry.
Ooh. No, that's the heart of it. But we got a few days before that.
Oh, word.
Yeah, yeah.
I was like, I'm so
You gotta give him credit. You did say whenever you ask a question, it's a really good answer.
It is. It
Someone
is.
shouted it out a few weeks ago.
Yeah.
And we were like, oh my god, yes.
All right. But here's another way we can get a better approximation. We were only using 4 rectangles. Okay? Let's increase the number of rectangles. So let's go ahead and again let's go back to the left endpoint method. We're looking at number 6 here. And let's do it with 8 rectangles. Okay? So we're going to go a little faster through this one. Here's the first rectangle. Here's the second rectangle. Third rectangle, etc.
You're doing the left hand then.
Am I?
Looks like it, yes.
It does look like it. Okay? And I did say to use the left endpoint method up in the
Did it say it up there?
Prompt, yep, right here.
Ah, we'll look at
It
that.
was hard to read, isn't it,
Look at
Alex?
it.
No, just joking. All right. So I'm going to start writing this, and then I'm going to get exhausted. So we're going to say that the area is approximated by L of 8, which is equal to F what? What is the first value that I plug into this? F of 1. Okay? Folks, if you don't have a picture, you need to sketch one. Okay? Because this is, I'm not going to say this is easy, but it's an exercise in sort of bookkeeping. It's not extremely complex, but it just requires that you be careful. So draw a picture to force yourself to be careful. Times, what's my delta x here?
1.
1. How do you know that?
9 minus 1 over 8.
Yeah, let's use that formula. We said that delta x is equal to b minus a over n. So the rightmost value is still 9. The leftmost value is still 1. But what's changed? The number of rectangles is now 8, and when you simplify this, you get 1, which is our delta x. Okay? Plus f of 2 times 1 plus, and I'm tired, so we'll just do f of, what's my last one? What's it going to be? F of 8 times 1. Be oh so careful jumping like that, though. Okay? That requires you have a good picture. By good picture, I mean you don't have to have an accurate graph. You just need to draw an abstract function, but you should subdivide it. Okay? All right. I don't like this. This is tedious. Well, eventually we will find we'll have a way to do this very well. But even before that, I can't even start to develop a theory because of this. This is just a mess, right? This dot 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 stuff, and it's a mess. I would like to come up with better notation. Okay? In math, a lot of times you've got an idea. We've got an idea. We're using area. We're using areas of rectangles to approximate the area of the curve. You need a good idea, and then you need good notation. Okay? And then you put the two together, and you can get somewhere. Okay? So we've got a good idea. Now we need good notation to be able to extend this. All right. Just as an illustration, though, for how we go forward, okay, we increase the number of rectangles. Okay? Now, I think that when I say increase the number of rectangles, that's the most obvious way to see how this is happening. Okay? But actually what we are doing is I want you to think of this as not increasing the number of rectangles, but decreasing the width of the rectangles. So the number of rectangles is becoming larger and larger. The width of the rectangles is becoming smaller and smaller. Okay? So I'd rather you think of it that way, but either way will kind of suffice for a little while. But you'll see where we need to be careful. Okay? So here we have this function, the natural log of x plus 1. I've graphed it for you. Okay? And I went ahead and I didn't do it. I told a computer compute R4, R8, R16. These are the right endpoint methods. You notice that? Okay. And these are the right endpoint methods. And each time I'm doubling the number of values, the number of rectangles. Okay. Something interesting to keep in mind here is that what's the width of this first rectangle? Yeah, 1 point something. We could actually find it, I think, right? Delta x is equal to b minus a over n, right? What's my b? 5 minus, what's my a? I think it's 0. Okay, that's all right. All over how many rectangles? 4. So I think we get 5/4 or 1.25 is the width of each of these intervals. Notice that 1.25 shows up here. It also shows up here as the right endpoint of the second interval. Okay? Because I am just adding more values into the partition here, notice that here I've got the values 1.25 and 2.5 and 3.75 and 5, and I forgot 0. Those are the values of the partition. This has those same values plus more. So we're going to call this a refinement of this, because we just added more values into the partition. Okay? So you could think of each one of these as a successive refinement, decreasing the width of each rectangle, which in turn, if I decrease the width, if delta x gets smaller, then for all things to remain the same, n has to get larger. Okay? And here you've got all the way up through R128. I know it's hard to read, folks, but it was the best I could do. So you can see that above you've got the estimated area, and then below that you've got the actual area. It's a little hard to read. Maybe you need your spectacles. But you're accurate to the 10th place. If you want to get more accurate, what do? Just add more rectangles, right? Okay. Then we could do the exact same thing with the left endpoint. How many rectangles do you see? How many rectangles do you see? I see 4. This is kind of a trick question, right? This rectangle right here has a width of 1.25, a base of 1.25, and a height of what? 0. So I know that people say, oh, I kind of dislike it in early math classes when they say apply common sense, because common sense really only gets you so far at math. If you guys had common sense, you wouldn't be here, actually. You'd be taking some other class, right? So we've already thrown that out the window. Anyway, I know that you can't really have a rectangle of 0 area, but what we're considering area here is simply a product of a base and a functional value. And functional values can be 0. So we are going to consider that area. Okay? So anyway, here are our rectangles, and it's the same idea. Okay? So here you get some verbiage on that. It basically just describes what we were just talking about. Okay? That we just further subdivide either the Rn or the Ln. That gives us more values in the partition, and so we get a refinement. And so that I think it should be clear now, if I were completely starting with a new partition, I don't know if this would be clear, but I think it is clear since I'm picking the same values that each refinement is a better approximation of the area. Okay? The interesting thing is, I believe, it doesn't even matter if you just increase the number of partitions, then you actually get a better refinement. But that's a topic we luckily don't have to get into. Okay, so it turns out that the true area beneath the curve is where did I list it? Is 5.75, approximately 5.75. Okay, and we could see then we sort of have a limiting procedure, right? Well, this is like the very first day of Calc 1 where I said, here's the idea. We're going to get closer and closer. There's this limit notation showing up, but now we need to spend a couple of days being rigorous about this. Okay, so this is the essential idea here for getting the exact area underneath the curve. Okay, go ahead and answer numbers 9, 10, and 11. Okay, Jesse already asked the question. Okay, so now I'm formally asking it. One of these was an overestimate, one was an underestimate, and I want you to talk about why that was the case. So talk with your group. So will the left endpoint method always be an underestimate? No. What causes this left endpoint method to be an underestimate? And let's to Jesse's point, let's only consider positive functions here. Okay. Concavity, maybe. I don't think it's concavity. What's that? I heard it actually. What? I think that's good enough. I think if your function is increasing, then the left endpoint method will always be an underestimate. If it's a positive function and your function is increasing, then when you do this method, because it's always increasing on that interval, you'll always be underestimating. And if you do, this was let's just call this A here, and here's B. And then if we did the same thing, A and B and the same F, but we did the right endpoint method, then the right endpoint method would always be overestimating. But if I make the function now decreasing, now do the left endpoint method and the right endpoint method on that.
Same thing, just reversed.
Vice versa.
Okay.
Switch them.
All right. I agree. Ooh. All right. Okay. Here it is. Warning. This actually goes to Jesse's question. In these early examples, we are computing the area beneath a curve in the x-axis between A and B. In all of these examples, our function f has been a positive function. That is, f of x is greater than 0 for all x in the interval. Okay? This avoids having to answer the question, what do we do when f is negative and we compute a negative area? Because then I'm going to have to be much more precise in the questions that I ask. Okay, and just to give you a hint of what's coming forward, I'll just jot it over here. So we'll see this in the next example, or in the next section. But the function f, when we do this approximation technique, we'll count that as a positive area, and this will get counted as a negative area.
So would you do like a net?
So we would call this the net area
Look at it.
if I want to consider it this way.
What's going on?
Yeah, you're stealing all my thunder here. No, you're just fine. You're just fine.
I'll leave.
No. This is good. This is good. Okay. Versus if I asked you for the total area, if I asked you for the total area between the curve and the x-axis, then you'd have to do some adjustment of our method to make sure that we get the lower values counted as positive.
Did you do like the absolute value of that, or not really?
Here you go. Come up here. Come on up. Yeah, that's exactly right. That's exactly right. But we also have to then know where to break it up. So you'd have to first find the points where the output's a 0, and then break it up into those segments. We'll see that going forward. Okay. So we're going to keep working with this notation here. And here I've already said what we want to do with defining delta x. We've already put this up on the board. Okay. But let's just go ahead and write out the right endpoint method and the left endpoint method. Okay. So we will always start calling the most left value. We're going to call it x0. Okay. It doesn't. I completely agree with you. It doesn't make sense to start calling the first thing in a list the 0th item in the list. But you can count it that way, right?
What if I was like, this is x15?
Well, then
X16.
you're just going to have a headache. Yeah. So this is actually done to simplify things down the road.
Kind of how
Yeah.
it works in computer programming.
Yep. Yeah. So something about what we're going to do should remind you a lot of some of the early computer programming operations you might do in a coding class. Yeah. Yeah, definitely. Okay. So then I'm going to call this value right here x1. This value would be x2. Okay. Folks, sometimes in math we need to talk about some arbitrary value in the middle. So I'm going to put ... Then this is going to be the xi minus 1 value. And this will be the xi value. Okay. ... Okay. This will be the xn minus 1 value, and then b will also be xn. Okay. So let me do this now. We can now go ahead and start making our intervals, right? So this would be the first interval. This will be the second interval. And then by the way we've numbered this is why we numbered it this way. This will make this abstract interval in the middle here, this would be called the ith interval. Okay. And so then what will the last one be? The nth interval. How many intervals do I have? 1, 2, n. I've got n of them. Okay. So that's, again, if I want n sections of fence, then I need n plus 1 fence posts. But I don't want to start counting call the first fence post the first fence post, because then that would make this the n plus 1 fence post, and that makes enumerating things a lot more difficult. Okay? So that's why we started out with the 0 and we end up at xn.
Would we ever do xi plus 1?
Well, yeah, it would be the next one over.
Okay, we could do that.
Yeah, we could definitely do that. But then the interval from here to here, if this is I and this is I plus 1, what's not obvious just when you just look at this, but when you've got it set inside the rest of our picture, is this would be the I plus 1th interval. Okay, so now we can write out Rn. I'm going to write out Rn this way. The right endpoint method says take the right endpoint of each of those intervals. So when it comes time to do the ith rectangle, what value am I picking? Yep, and what's it called? We're going to evaluate this where? I mean, that's what I'm asking you. Where are we going to evaluate for the ith rectangle, we're going to plug in x. Is it? So so for this first rectangle, we picked the what value? The right endpoint of it.
Oh, for the right, sorry. X.
Yep. And so then what's this one?
XI.
The xi value, delta x, plus dot dot dot, plus, what do we pick for our last one? Xn delta x. Can you see us actually selecting the right value of each method? Or excuse me, the right value of each interval. Okay. Folks, I'm just showing you how that, so this is what I'm trying to spend a lot of time on is talking about a very difficult topic that is only difficult because we're people and we're bad at counting. Okay? That's all there is to it. We're bad at this. It's not that it's a hard idea, but pretty soon we're going to start stacking ideas on top of this. So I'm spending a lot of time trying to focus on how we enumerate these things because I know that we all struggle with it. But at some point I also need you to say, hey, this is a counting issue, and I acknowledge that I'm bad at counting. Okay? Because we all are. Okay? All right. All right, so then for our left endpoint method, we're going to take what value? X of 0 delta x plus f of x1 delta x plus dot 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 plus f of x I minus 1 delta x. This is the ith rectangle. In both these cases, the ith rectangle, but it looks a little different because we're using the left endpoint method here. Plus dot dot dot. Here's our nth rectangle, f of x n minus 1 delta x. All right. So we spent a lot of time on that. I'm trying to head you guys off before you go down the wrong way. Okay, because it's easy to make some mistakes doing this. Any questions? Awesome. All right. So I said that we've got an idea down. We're trying to start developing some notation. One of the reasons why I had to get very careful in our enumeration notation is because soon we're not going to be looking at any pictures at all. Okay? We're going to be doing this without looking at pictures at all, so we've got to be even more careful with the way we write things out. My next goal is to introduce something called summation notation. Okay? Usually about 2/3 of the students have seen summation notation. How many of you have seen summation notation? Yeah. Okay. So happy. Okay. I wish you hadn't, but that's okay. We'll start. I'm going to treat this as we're starting from scratch because that's the best place to start. All right. This is whenever you find yourself writing out a long summand, meaning a long expression with several terms separated by addition. Okay, if there is a pattern to how you're getting those terms, you could express it in summation notation. Okay? In my opinion, if ever you find yourself writing a dot, 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 it probably means you could shortcut it by writing summation notation. Okay? So we're going to learn how to do this. All right, the first thing is the letter that shows up here. Okay? This is the Greek letter sigma. Okay? Everybody does it to varying degrees of awfulness. That's about the best you'll see me do it. Okay? Everyone does their own sigma. It's worth practicing just a little bit. Don't spend too much time on it. Okay? But practice just a little bit making your sigmas. You certainly don't have to make it as nice as the print face ones. Okay? Why do we use sigma? Okay? This is silly. We use sigma because sigma is the Greek letter S, and summation starts with the letter S. That's the only reason why we use that symbol. Okay? So it's an S. It stands for summing things up. Okay?
Bunch of mathematicians wanted to be fancy.
Yeah. Okay. By the way, someday if you go on in math, you'll see product notation, and product starts with the letter P, and so we use the symbol pi, a capital pi, not the curly one, a capital pi for product notation. Okay. So just to give you a sense of silliness. All right. Now, for those of you who've written some computer programs, this part's going to seem a little intuitive. Okay. We've got this summation notation. Okay, this sigma stands for add them up. We're going to add up a bunch of things. Well, the first thing we should ask is, where do we start adding from? And so that's what, well, actually, before we even do that, this I here is our counter. Okay, for those of you who've written a computer program, that the word counter may make sense. If not, the actual, what we'll use in math is we'll call it the index. Okay? All we're doing is we're taking a long string of things and we're indexing it. Okay? We're applying an artificial ordering system to it. Okay? We're indexing it. All right? So this is the index or the counter, and this is the start value for our counter. That's the start value for our counter. Okay? This is the stop value. Then what are we going to add up? We're going to add up that's something that depends on some formula of our counter. So this is some formula involving I. And let me not use I, let me say the counter. Because in different problems we will use different letters to denote our counter variable. Folks, it is really important that you spend a little bit of time getting comfortable with this. Okay? I know the truth is that some of you are going to see, we'll work with summation notation for the first two sections, then it'll kind of disappear in the background, and then come the test, you'll look at this and your eyes will go see just one big monstrous mess and you'll go, oh, I don't know what that is. Okay? So spend some time with it so you get comfortable. But then also, if, there are times when I'm looking at a monstrous summoned in a math book, I don't know what it represents. So I just start writing out some of the terms of it until I start to notice the pattern that the author condensed into that summation notation. Okay? So remember, at all times, this is actually, whether you believe it or not, meant to make your life easier. Okay? So if you're ever confused, go ahead and unpack it. Pretty soon after you've written out 20 terms of it, you'll say, wait a minute, there's an easier way to write this. I'll write it just like this. Okay? All right. So let's go ahead and get started. We'll do this first one together. Okay? So here I've got a summoned. It means add up a bunch of things. What am I going to be adding up? I'm going to be adding a bunch of 2 times a number plus 1. I'm going to repeat that operation, adding it each time. Okay? So my index here is I, and where am I starting this at? When I is 4. So the first entry looks like 2 times 4 plus 1. We have now written out the entire formula where I is 4. Then we put the plus sign that the summoned represents, and we move our counter value up 1. So now who is I going to play the role of? 5. So this next one is 2 times 5 plus 1. We've written out the entire formula that we were taking the summoned of, playing with I playing the part of 5. We add 1 to our counter, and we repeat. Okay. When do I stop this? When I become 7. So here's the last entry. Okay. Yeah.
So if we start at 4, wouldn't we assume that we're doing like the left point?
Oh, so careful. At this point, if you've seen some more of the story, at this point, I am not. This sum in is just an exercise. It's not being. We're going to eventually use to Tyler's question. We're eventually going to use summation notation to express these sums of rectangles. Yeah, so we're getting there. Right now, we're just playing with this. We're just trying to get used to what is this crazy looking sigma thing. Yeah, great question. Okay. So help me out, folks. I think we get 48.
Yep.
Okay. All right. So I would like you to now in your groups do them in this order: B, C, then E, and then do D. Okay. I don't know why. Someday I'm going to switch these two around. Okay. So do B, then C, then E, and then if you feel like it, go back and do D.
Is that L times L? Is that
Yep.
L times those two parentheses?
Yes, yes, yes.
Yeah.
So inside the formula for L, you could have whatever operations you want. Multiplication, powers, factorials, square roots.
You said B, C, and then B?
Let's just do it like this. 1 times 2 times 3 plus 2 times 3 times 4 plus 2 times 4 times 5.
But you have an N, right? So.
We don't know what n is.
Exactly.
So although this does represent some compact idea, we can't actually write it all out without knowing what n is.
So what would we do?
Well, just what I did.
So you're just like, oh yeah, here's the start and then
Yeah.
question mark.
Yeah,
Okay.
yeah, yeah. Because eventually we're going to vary n. We're going to vary that upper limit. What do we get for this for E, folks, if we actually crunch the numbers?
36.
Yeah, I think we get 36. Adding those up. Remember that, because we're going to need that for another problem. Okay, folks, I am very unconcerned if you get hung up on D. D will not show up on a test, but I just want to show you how this summation notation can be built inside of itself and get more complicated, because eventually you're going to need this. Okay, if you go on to take Calc 3, or if you go on to take linear algebra, you'll be using summons like this. Okay. So let's go ahead and write out so this is how I'm going to do this, folks. I'm going to show you sort of this is going to look a little bit messier than it needs to be. I'm going to show you one way that is, although it's messy, it's the most intuitive. And then I'll show you a different way to write it. Okay? So the first way to think about it is, I'm going to start off with J being 2 and K being 6. Now, working inside of this summand here, I'm going to keep J stuck at 2 while I run through this summand. So then I'm going to tick up K by 1, and so I've got 2 times 7. Okay? Now I'm at the top of that, I'm at the end value for that sum, and so then I start over with J, and I tick J up 1, and I reset K. And then I've now exhausted the inner summand for K, so then I tick up J 1 more, and I reset K back down to 6. Okay? We've got a nice little mechanical procedure spelled out in a very compact way. Okay? Remember, folks, and I'll say this again for all of you, especially if you go and take more math classes, notation is meant to make your lives easier. If you're not getting the notation, you need to stop using it, write it out in longer form for a while until you get a little bit bored with it, and then say, boy, I wish I had a more concise way of writing this. Then you're ready to use the new notation. Okay? All right. Here's another way to look at this one. Okay? Another way to look at this is to call this the summand from j equals 2 to 4 of, and then inside of here, I'm just going to do j times 6 plus j times 7. You see what I did there? I went ahead and evaluated this sum right here, just leaving that as a j, and then expressing this as a 6 plus 7. Okay.
Get a little scrunched in there, but.
Yeah, I'm sorry, that's
So
hard to
it's
read. This is j equals 2 to 4 of j times 6 plus j times 7. Where did that j times 6 plus j times 7 come from? I evaluated this right here, just leaving that j without substituting anything for it. So this piece right here is this piece right here. Okay? But then we could go ahead and go one step further, and we do sort of a distributive. This is mimicking your distributive property in a lot of ways, and we get 2 times 6 plus 2 times 7, and then plus 3 times 6 plus 3 times 7 plus, now I'm definitely out of room, 4 times 6 plus 4 times 7, which is grouped the same way, but it's kind of just a little bit different way of thinking about it, which is, I think, in some ways easier as time goes on. Yeah, Maria.
Would you simplify what's in the parentheses? J times. Okay.
Oh, yeah, great. Yeah, so there's many properties you can use here. What is j times 6 plus j times 7? It'd be 13j. Yeah. And then you could go ahead and work with it like that. So yes, in fact, I should have seen that. Yeah, that's a great way to do it. Okay? So there are many ways to do these. Okay? And because really summands are just addition, you have lots of properties of multiplication and addition combined together. There are lots of ways to do these. Okay? All right, so again, I'm not gonna give you one as hard as D, but I just wanted to show you that because if you go into any other classes, you're going to see double summands. Okay? All right. In some cases, we can evaluate certain summands with a shortcut formula. Okay? That just relies upon knowing the terminal value of the summand, the final value, the stopping value of the summand. Okay? So it turns out that if I want to add up the integers from 1 to whatever, I can use that formula. Okay? So this is a great bar trick, right? You ask your buddies to add up, numbers 1 to 100 and see what they get, and then you just sit back, and when they're about halfway through, you do this calculation. It kind of depends on what sort of bars you go to, what sort of friends you have. Sure. Okay. Anyway, let's just see how this works. We added this up once before, and we got what? This one right here. We added up this once before, and what did we get? 36. Let's use this summand formula. It says we could just take 8 times 8 plus 1 divided by 2. Well, that's 8 times 9 over 2, which is equal to... Don't know what happened there. Which is equal to 36. Okay. There are other ones. Here's a formula for I squared. It's not quite as nice, but it works. If I want to sum up, let's just go ahead and do this two ways. If I asked you to sum up from I equals 1 to, let's just go to 4 of I squared, that would be 1 squared plus 2 squared plus 3 squared plus 4 squared. Help me out, folks. What does that come out to be? 10, 16, 20, 30, I think. Does that come out to be 30? But let's do it using this formula. Okay? So I claim that if we wanted to sum this up, that we could just use this formula. We could use the formula where we do 4 times 4 plus 1 times 2 times 4 plus 1 over 6. Let's see, that's 4 times 5 times 9 over 6. And sure enough, it's 20 times 9 is 180. 180 divided by 6, that gives us 30. How are we doing? Okay. Certainly this formula didn't really help you for this short one, but eventually it would be helpful, right? If n were 100, this would definitely save you a lot of time. Yeah?
So that where it says holds for 3, 4, and 5, it only works for those 3.
No, and sure enough for all others. Also holds for all
But
n's.
did you just evaluate the number 4 right there?
I only did it for 4. Yes.
But if you had done it for 3,
It would have worked.
and it would have been
Well, it would be one fewer than this, so it would be
3 times 3
14.
plus 1 times 2 times 3 plus 1 over 6.
Yes. Yep. So all that matters here in this, if you look at the formula, is the upper value. That's what you use as your n.
That's cool. That's very simple.
All right. So we're trying to develop this notation, but we're going to take a break here. Yeah, let's take a break. We'll start back up in 10 minutes. Our goal now that we have this summation notation is to return to the work that we were doing earlier to try and make it more compact. Okay? So let's go ahead and here was our work for the very first example when we did the left endpoint method with 4 rectangles. This was the work we had developed. Let's go ahead and try to write this in summation notation. So we would say that this is the sum from I equals 1 to n of f of I delta x, which we could then write as the sum from I equals 1. Oops, I'm sorry, I made a mistake here, folks. I put n, but we know what n is in this problem. What is n in this problem?
9.
So n stands for the number of rectangles that we have. So n is 4. So this would be f of I times delta x, which is, what is delta x in this problem? The delta x was 2. Okay? So this, and you may not agree that this was a time saver, but this expression right here, if you were to unfold it, would look just like, well, I got to be a little more careful here. I'm sorry, I'm on autopilot and I shouldn't be. We need a kind of a formula for coming up with what I is. So, folks, let's please reset that because I am dead wrong here. This is f of what? Well, we want to go from 1 first, and then 3, and then 5, and then 7. So I think I want to do 2I minus 1. Check that.
Why wouldn't the formula be I equals 1 to 9 and then the f of x squared plus 3?
Oh, you could do that. You could do that. I'm going to do it this way.
Oh, okay.
I'm going to do it this way. Yeah, so there's lots of ways we could do this. Delta x equals the sum from I equals 1 to 4 of f of 2I minus 1 times 2. Yeah, just check. So, by the way, folks, this is a good exercise for what you'll be doing. If you have trouble coming up with a formula, the best thing to do is to just guess something and then check it and then correct it if needed. Okay? So, for example, I've claimed I've got a formula for what these values should be. When I is 1, I want it to spit out a 1. When I is 2, I want it to spit out a 3. When I is 3, I want it to spit out a 5. And when I is 4, I want it to spit out a 7. Well, let's check a few of these and see if I got it. Okay. So you see how you can work with these? By the way, that's a handy way. I think I've mentioned this in class before, but 2n plus 1 or 2n minus 1 is a handy way to give yourself an odd number, to guarantee that a number will be odd. Because if you double a number, it guarantees it'll be, well, more than positive. If you double a number, it guarantees it'll be even. And then if you subtract 1 from an even number, it guarantees it'll be odd. Or if you add 1 to an even number, it guarantees it'll be odd. Okay? All right. So the next thing I want to do is I want to define a partition. So we've mentioned this before. A partition of size n on the interval from a to b is just an ordered set of n plus 1 values. So it's got to be ordered. And we'll start with a, but we'll label a as x naught, and then we'll do x1, and then we'll do x2, dot, dot, dot. Let's go ahead and do xi minus 1, xi, comma, dot, dot, dot. And then we do xn minus 1. And then with the last one is xn, which is also known as whom? Yeah, what is the right endpoint? B. 7. Oh, you're looking up here. You're
Sorry,
looking up there.
yeah.
That works.
I
That
don't
works
know.
for the previous example.
Yeah,
But
so
we're just doing this
they're right.
abstractly.
Okay.
Yeah. Would it work for the last example?
Yes.
Okay. All right, so let's answer these questions. So what intervals correspond to the partition above? So this would be the interval from x naught to x1, and then the interval from x1 to x2, and then the dot, 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 then the interval from xi minus 1 to xi, dot, 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 and then the interval from xn minus 1 to xn, which you could also label as b. I'm not going to be consistent. Sometimes I'll put b, sometimes I'll put xn. Any questions about that? Okay. So again, it does seem strange that we started at x0, but then that enables us to call this the first interval, which is really what I'd like to be able to do. This is the first interval, this is the second, this is the ith, this is the nth. And I get to name them all that way because we started counting at x naught. Okay, so what intervals correspond to the above set? Well, we had the interval from 1 to 3, and then we had the interval from 3 to 5, then we had the interval from 5 to 7, then we had the interval from 7 to 9. Okay. So what partition did we use in the first example? What was our partition? It was 1, 3, 5, 7, and 9. Notice how many values are in that partition? 5, because we had 4 rectangles. Okay? All right, I talked that to death. All right. So let's go ahead and try this one more time. I'm not sure what I want to do here. I guess the only thing I would say is if we use the summation notation, we could say this is a sum from n equals. I want to always, I always want to start my counter at these. This is a good thing to keep in mind. Following the book's choice of notation, I will always start my counter at 1, but then adjust accordingly if I want to talk about some other value. Okay, so I'll start the counter at 1, we'll stop it at 4, and so then I'm going to call this f of xi minus 1 delta x. Double check me here. In this interval, in this partition up here, when x is 1, we label that as what? X what? X of 0, x naught, right? So when I want the 0th value from here, I put I minus 1. Does everyone see that? Because I starts at 1, and when I put a 1 there, I get 1 minus 1. Okay? And then this is the x0, the x1, the x2, the x3, the x4, and I want to only include the x3 value. Well, this still stops at 4, but then I do 4 minus 1, and so the last value here is the x3 value. So if we expanded this summation notation, it would be f of x0 delta x plus f of x1 delta x plus f of x2 delta x plus f of x3 delta x, where this last f of x3 came from when n was 4, or when the counter was 4, we had 4 minus 1. Does that make sense? I like that our author does this. Most calculus books do not show you partitions your first time through. But it's a good idea to see your first time through. So I like that our author does it, but it sure makes for a much longer introductory section. Okay. We're going to add one more ripple to this. First of all, for all examples you do, we will use a common width for all of our intervals. Okay? But there's actually nothing that says we have to use a common width for each one, which means we can have several different delta xi's. Okay? So there's nothing that says there has to be an even dispersion between x0 and x1, and then from x1 to x2, and then from x2 to x3, etc. There's nothing that says it'll have to be of even width. You can still do all of this calculus that we're doing right now. You just have to ensure you've got an ordered list of values. That's all it has to be. Okay? So we always, in the examples I give you, will always have a common width just because it makes the calculations much easier to work with. Okay? But when I give the abstract definitions, I'm not going to assume that we have a common width. Okay? So here, delta xi would be what? How would I figure out the width of the ith interval? Well, I would take xi minus xi minus 1. That's a subscript minus 1. I'm going to write this big off to the side. I know that's... so this is xi minus xi minus 1 all over... Actually, that's it. That's it, right? That's its width. That's the width of the ith interval. Does that make sense? So what is the width of this interval? Well, you just take where you end up at and subtract where you started from. That's how wide it is. There's no divided by n here because we're not trying to ensure that these all have even, these are evenly dispersed, that these have the same width. Okay? All right. So everything we've been doing up to this point has a name. Okay? They're called Riemann sums, named after mathematician Riemann. I don't remember his first name. Sorry. Okay, they're named after Riemann. Okay, and this procedure, doing these things, are called Riemann sums. So we've got left Riemann sums. That's the left endpoint method. The Riemann sum with the left endpoint method. Right Riemann sums. Okay, etc. Okay, so here we go. If we've got some function, so this part's very abstract here. If we've got some function defined on a to b, okay, yeah, we can always do this. We can always give a partition. And then when we give that partition of size n, it gives us the intervals that go from x0 to x1, comma, x1 to x2, comma, dot, 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 comma, xi minus 1 to xi. This part's getting a little redundant. Comma, dot, 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 comma, xn minus 1 to xn. Those are the intervals it gives us. We can always do this. For any function, we can do this. Okay. So, I want to define the left Riemann sum. Okay, so the left Riemann sum for this function is this sum right here. We're going to take the sum, and I've chosen to the book's notation here. So we're always going to start our Riemann sums at 1. So it's going to go from I equals 1 to n. We'll always go from 1 to n. Okay? But then what do you plug into the function? That's a little bit different. We're going to take xi minus 1 for the left Riemann sum method, delta xi. What is delta xi? The width of the ith interval. Folks, I know that at this point, this notation, I mean, no one step of this notation is all that challenging, but we've added it up, literally and figuratively. We've been adding all this notation together, and it's starting to get a little overwhelming. Okay? When I look at this, let me tell you what I see. When I look at this, I see a base of a rectangle times a height of that same rectangle. I calculate the area of that rectangle, and then I do what? I add it to all of the others. So I need you to look at this and to see that it's just, this to me, it looks like adding up a bunch of rectangles. Can you see it? It's a height times a base. Then take the next rectangle, which has its own height and its own base, and you do that there. Okay? And we repeat this. Okay? So the next one is the right Riemann sum. Okay? And so this is, and I can't fit it on here. I don't know what I was thinking. I'm going to write it over here. The right Riemann sum is the sum from I equals 1 to n. This time we just take the xi value, because we're using the right endpoint method, so we just take the value that's at the right endpoint of that interval, which is the one we want. Good. Delta xi. So the only real difference here is that I'm now using delta xi, the width of the ith interval, because there's nothing that says they have to have even width, even though all problems I give you will do them with even width. Okay? So then I could give just the general Riemann sum. So just the Riemann sum, or let me say it like this. I should say a Riemann sum. So what's different here? I'm not specifying how you select the value from the interval to plug into it. Okay? So when I write this one out, and again I'm out of room, are you guys able to fit these in your notes? You could use a little more room? Okay, I'll try to fix that for next semester. All right, so sum from, again, I equals 1 to n. I've set it up so that they always go from I equals 1 to n. But then we're going to take f of xi star delta xi star, or delta xi. Still can't fit it. So that's the sum from I equals 1 to n of f of xi with a, I'm going to put a star, I'm going to, folks, I was supposed to be using k's for all these. I'm not going to change it. We'll change this to an I, and this to an I. Great. And this to an I. This to an I. It doesn't matter, right? The choice, so these are dummy variables. The reason why the author uses k is because we've got an I in here already, and technically I should not use that letter again. Okay. All right, times delta x I. Okay. What does this star mean above here? It just means that it's just an arbitrary selection from the ith interval. Okay. So if you go back to our very first example, I know it's been a little while. If we go back to our very first example, if you remember when I was drawing these rectangles, don't change this. I said we could just pick any old x star value from in there, and we could still do the exact same thing. And then for this rectangle over here, we could take a completely different x star value. Maybe this will be our x star value for this one. And we go up to where this one intersects the curve, and that's how we construct the rectangle. Okay? So this method works regardless of whether you're saying no, you must pick the left endpoint of the interval, or you must pick the right endpoint of the interval, or the midpoint, or just any old value in that interval. That's what this most general one is saying. It doesn't matter which one you pick. Okay. Then I'll just give you the midpoint Riemann sum. Sum is, it's the same summand. Everything's exactly the same. I equals 1 to n of f of xi, and then our author puts an m there. M for midpoint. So you take that interval, okay? You take the midpoint of that interval, and that's what you plug into the function delta xi. So how would we find the midpoint of an interval? We would take xi minus xi minus 1, and we would divide that by 2. That would give us xim, the midpoint. Don't let your eyes glaze over on that, folks.
Is it xi minus 1 or minus 2?
Oh yeah, you can let your eyes glaze over.
xi minus 1.
xi minus 1. Exactly. So for example, if this were my interval right here going from 7 to 9, how would I find the midpoint of that? Oh, folks. That should be a plus sign.
There should be a plus sign at the top
Just here. Just here. That's because this gives us a formula for finding. No, it shouldn't be for the width. No, because what I'm doing here is I'm not finding a width. I'm taking an average. I'm averaging the two values. So we would do 9 plus 7 divided by 2, which is 16 divided by 2. Sure enough, the midpoint of this interval is 8. But abstractly, we took the one endpoint, added it to the other endpoint, and divided by 2. Folks, sorry to mess up twice at least, writing that out for you. Any other questions? I hear. Jesse, did you have one?
I'm just wondering, xi minus 1, that's just because it's the 7's is smaller, correct?
Yeah, you could have actually interchanged. Once you've got addition, you can interchange them. So it could have been xi minus 1 plus xi. That might be a more methodical way of writing it out. Yeah.
So we do xi minus 1 xi, and then we have xn minus 1 xn. They're just essentially kind of the same.
Yeah. So the reason why I have this because this is specifically though the last interval. This stands for some interval anywhere on the inside. Yeah. So there's nothing general about it.
So n is the last.
N is always the last one. Yeah.
So the x1 and x2 signify the first
Yeah.
interval.
Mm-hmm.
The xi's are the middles-ish. whatever
Some
they are.
some random one in the middle.
And then the n's are the n.
Yes. Yes. Good. Good. Well said.
Oh, boy.
Yeah. Okay. Folks, at this point we've done all we need to for this section. We'll do some more practice here in just a second, but I want to give you sort of a motivation for why we're trying to find the area underneath the curve. We're going to find out that it turns out there's tons of applications to being able to do this. Like there are just, you couldn't count the applications, but let me give you one that's readily accessible. Okay? So we know that distance is equal to speed times time. Suppose a car travels at 50 miles per hour for 4 hours.
Seats tight.
Well, if I think of the velocity function as a constant 50, v of t equals 50, okay? And we say, okay, what does this car do between the hours of 0 and the hours of 4 during the first 4 hours? Well, what's the area underneath this curve? What's the area underneath that curve there?
What was the height?
How many
200.
4 hours.
Okay.
We're at a height of 50.
200.
200, right? The area underneath the curve is 200. What's another interpretation for that 200? It's the distance that you travel. It's the distance that you travel, which is the distance traveled. Okay? I had a teacher once, he said, I see distance as an area. Well, that works in a lot of applications, not all applications, but I think that's a good thing to think about. The distance that you travel, okay, let me just say this, let me just reiterate this one more time. Okay? The distance traveled is basically, let me be a little careful here, basically the area under the velocity. In fact, if I want to be exact, right, I could be exact. The distance you traveled is the area under the speed curve. Your displacement is the area under the velocity curve. That's a silly issue that we'll worry about on the next section. All right. Oh, how did this happen? This was all supposed to, there it is. Sorry, folks, I don't know how that broke. Anyway, here it is. Here's the picture. Wow, this is a lot nicer than the graph I gave you. All that information that I just gave you, you could put there. Sorry, I don't know how that got broken up. I was fiddling with things this morning and goofed it. All right. So let's motivate this a little bit more. In the previous example, the speed was constant. But what if the speed wasn't constant? Well, you would still say that the area underneath the speed curve is the distance you travel. So you still are interested in finding the area underneath the curve, even if it's not a nice horizontal line. So that's supposed to be motivating where we're going. Okay. I don't think I'm going to just set this one up. Okay. Approximate the area underneath the curve. This is the same curve we've been visiting. By the way, pay attention to this because I'm going to revisit this curve twice more. Okay. X squared plus 3 from x equals 1 to x equals 9 using the midpoint Riemann sum method. So here we go. Here it is. Here's 1 to 9. Here's our partition. Right? These are our fence posts. That's our partition. Okay? And then what we've said here for doing these Riemann sums, we just have to make sure we take a value from within each interval. Okay? In the right endpoint method, we take the right value. In the left endpoint method, we take the left value. And in the midpoint method, we take the middle value. So we go up to where the middle value intersects the curve, and we draw it, the rectangle. Okay? The midpoint method is always a better approximation than either the, I don't know if I can say always. I think I can. For most curves we deal with, I don't know if I want to say always just yet. I haven't thought about it. But is generally a better approximation than either the left or the right on its own.
Wouldn't it normally, I would think you could almost argue that based on the fact that you're always going to have an over approximation with an under approximation, so you're going to get closer. Is that,
Well,
that makes sense?
but I mean, if I gave you a curve that was doing this, and you picked the midpoint always at a place where it was dipped, I'm not sure. So I'm a little hesitant. I don't know. Without thinking about it some more. And I don't want to. Yeah.
So, say with the graph you just drew, the arbitrary one, could you do overlapping of the rectangles technically?
You never want to have overlapping of the rectangles. And that is, so when we form the partition, there is some overlapping values.
But not the actual area.
But so the most you would ever, I guess the most you could ever do is, let's say this goes from 1 to 2 and this goes from 2 to 3. Maybe in this one you pick 2 and in this one you also pick 2. That could happen. But then in the next one, there's no way you could pick that 2 again. So there is the possibility of overlap, I guess, but it would only happen at the endpoints. Yeah. Okay, I think I want to stop. This is just some more examples here for you to take a look at and practice. You'll get plenty of practice of this in your homework. Okay. But there's not. This is just extra practice, and so I want to move on.